So what happens, for example, 1, if you're trying to figure out the definite integral of an absolute value function? I've already talked about the fact that you can't explicitly find the antiderivative of an absolute value without splitting it up into pieces. The same goes true for the definite integral. Since it involves the antiderivative, you've got to take whatever's inside of those absolute value bars, split it up into pieces. So this one's asking for the definite integral from -3 to 2. Let's take a look at two separate graphs here to give some context. Over here on the right is what we're trying to find the definite integral of. So if we just shade this region, we're trying to find the definite integral, the area under the curve between -3 and 2. So basically these two triangles right here. Now you could actually just use geometry to solve for these using the area of a triangle. But what if you had a different function inside of the absolute value bars, something like a trig function or a quadratic or a cubic? You certainly would not be able to use geometry. So what we can do is realize that y equals x is a function that we can find the antiderivative of. Notice the only difference between these two functions is that the graph on the left has a piece that's below the x-axis, but these two have the same area, except this one's negative. So if we could just find each of these individual areas and make both of them positive, meaning take the absolute value of those areas, we would in effect get this area over here of y equals absolute value of x. That's exactly what we're going to do in this lesson. So step 1 is going to be determine where your graph crosses the x-axis. Now the way to do that for an absolute value function is just to set whatever's inside of the absolute value bar equal to 0, and that will give you where it crosses the x-axis. So since it's just x inside of the absolute value bar, x will be equal to 0. Step 2 is going to be to break up your integral in terms of several pieces, depending on however many x-intercepts you have. If you have one x-intercept, you're going to break it up into 2 pieces. Okay, so basically you have this piece on the left and this piece on the right. If you had 2 x-intercepts, you'd have 3 pieces, so on and so forth. So we're going to find the definite integral of our absolute value function from -3 to 0, which is going to be our first piece. So again, 0 breaks up this integral into 2 pieces. Your lower bound goes here, then your x-intercept goes up here for your first piece. The second piece, your x-intercept goes down here, and your upper bound transfers over to your last upper bound of your last piece. And so still though, even though we have these 2 different pieces, we still cannot integrate an absolute value of x directly. But based on this concept we just talked about, we can split it up into 2 separate pieces where the absolute value bars are on the outside. Let's take a look. So here's what we're trying to find the definite integral of, -3 to 0 and 0 to 2. But as we said before, why not just take the antiderivative of y equals x, find its definite integral, and take this triangle, whatever this area is, make it positive, and that will ensure that that gives us the area under the curve for our absolute value of x function. Now for the pieces that are above the x-axis, it won't hurt to take the absolute value of them either, since it's also going to give you a positive area. So I kind of wrote that out here in this orange. This step only works because the signed area of the absolute value function on an interval with no x-intercepts equals the net area of the function without the absolute value. So what that means is we're just going to find the definite integral of this, put the absolute value bar around it, take the definite integral of this, put the absolute value bar around it, and that will give us this area over here. So that's going to look like this. The absolute value bars will just be moved to the outside of the integral rather than being on the inside. Now that we're doing that again because now we can take the antiderivative of x. So basically what we're doing is just taking these absolute value bars and moving them on the outside. Alright, so now we're going to evaluate the definite integral. So you antidifferentiate x now, which is 1/2 x squared, using the reverse power rule. The first one is from -3 to 0. Again, it's broken up based on that x-intercept. The second one is the same antiderivative, but it goes from 0 to 2. Alright, so to find this definite integral, you plug in 0 for x, that's your upper limit, then subtract when you plug in negative 3 for the lower limit. And to change that to negative, give me 1 second. And in fact, it won't matter because it's being squared, but that should be a negative 3. Okay. For the second one, you're plugging in 2 for your upper limit and then 0 for your lower limit. Alright, so when I plug in the first one, I just get absolute value of negative 9/2, which is just 9/2. Again, it's going to end up being positive. And for the second one, I get 1/2 of 4, which is 2. So we get 9/2 plus 2, which is the same as 9/2 plus 4/2, which gives you 13/2. Now 13/2 as a decimal is 6.5. You will always get a positive number when you're finding the definite integral of an absolute value function. That's because an absolute value function is always above the x-axis. So basically, what we've figured out is this net area, which actually is going to be total area for any absolute value function, is 6.5 or 13/2. And again, you actually could have figured that out by finding the area of this triangle and adding the area of this triangle. However, as you'll see in the next example, you have to be able to do it this way for functions that aren't as simple as y equals x. That's it for this example. If you have any other questions about it, let me know.